Kappa is the loss in the material, all right? And the imaginary part of the dielectric function is 2nk, if you want to transfer back and forth between those things. Typically, the measurables, the things that we, oops, I erased everything now. The thing that we actually measure is the index of refraction by measuring a refraction angle or a reflection intensity. We don't measure the speed with which the wave moved. We'll look at a phase shift, for example, but not speed. So we measure the index of refraction, and we measure alpha normally. All of these other things are derived from those measurements, right? But the thing that we calculate fundamentally is the dielectric function. All right, so I want to talk about dielectric function. In a simple model, yeah. So back to my atom. I have a nucleus, an electron cloud. That thing polarizes when an electric field is incident upon it. And we can just ask for the relative response of the electron with respect to the proton. For an applied electric field, the electron is going to move about 2,000 times further than the proton moves. So we'll only worry about the electron response. So the motion of the electron, when excited with an electric field, is going to be proportional to, and I'll just write am I going to deduce anything? No. But you have done this. Let me see. You've done a mass on a spring driven with a weak sinusoidal force to extremis in theoretical mechanics, I expect, or something, maybe differential equations. So I'm just going to state the result. So I'm driving a mass with a restoring force, and there is a natural or resonant frequency to the system, to come back to Adam's question. So I'm driving at frequency omega. Oops, yes, that's right. And my electric field is driven electric field as a function of time, which is a sinusoidal field. And the amplitude of response of position depends upon the magnitude of the charge, so that's the force, and the mass. Okay? And where you are in frequency with respect to the natural frequency. So that's one atom. All right? What we would want to do is we're going to add a whole bunch of those together, and we add a whole bunch of those together. I've got the polarization as a function of time due to one atom. Now I'm going to add up a whole volume of atoms. But I'm going to add them up over a small enough volume that, so I'm going to have bazillions of them anyway, but they're all going to be in a volume small enough that, for example, for a plane wave, maybe I'll confine them to 1/10 of a wave in distance. So that would be, let's say, 100 nanometers, which might be 500 atom pairs, atoms, right? So in a typical crystal or in a typical solid material, I'm going to have 500 atom pairs that I would consider all to be responding together, right? They're in a small enough volume that we'll just treat them as though they're responding pretty much together. So that's the polarization of an individual atom. If I want the overall polarization of the material, it's the density of atoms times the polarization of the individual atom, right? And I know that that polarization, I haven't written it down here, is related to the dielectric function of the material. Right? I apply an electric field, I get a response of the material, and I forgot, let's see, E D is equal to E plus 4 pi P, or something like that. That
No.
looks what? Plus, minus, what's a month for X?
It's minus from, that's plus for the,
It's
black.
plus for the D field and minus for the H field.
Yeah, so I just want to give you the idea that if I know the polarization, I can calculate the dielectric function. Okay? I'm not going to actually do that here. I'm just going to state the result. What?
Line's upside down.
Yes, you are right. It is upside down, even now. Okay. So I can write that the dielectric constant of the material is going to be, oh, which now depends upon driving frequency, is going to be, I'm going to put that in for vacuum just in case anybody wants to use it. Plus Q squared here's the important part. And there's, let me see. I haven't introduced loss, I'm going to add it in here. Because you solved the differential equation anyway, so. Gamma, the damping factor in the differential equation. So I've included a damping term here. So what do we know? Epsilon is equal to n squared is equal to, if we write it all out, 1 plus q squared n over m. I might have gotten the normalization wrong, but I'll check it and post it. So, but this is the idea. So we really are just talking about the response of an oscillator to a driving force. Damping term.
two pages.
That. So I've got a real part and an imaginary part, which vary as a function of frequency for the dielectric function. All just coming from a driven oscillator with a natural frequency of omega naught, right? And a damping term gamma. So what do those look like? I have them plotted out very nicely.
Are those gamma squareds
Say what?
in the bottom? Should they be gamma squareds?
I don't think so.
But
I don't remember. It sure looks like they should be if I were to square.
You have minus.
no, if you take the complex conjugate.
I'm going to leave them the way they are in my notes now. I'm not going to change it. I think that's right, but I don't remember.
You've left out a factor of 4 pi.
Yeah. Oh, you mean he does this in Ohania?
Yes.
Oh. I should read the book. Then I'll get it right.
Well, I'll be here for the summer.
Does he have sketches of the dielectric function in there?
Yep.
What? Yeah?
Yep.
Huh. I spent time fighting with Maple to get these. I gotta put up here.
What chapter?
So,
12.
Frequency,
Looking at 12.
real part of the dielectric function,
So his does.
One.
This doesn't have to enter, does it? Oh, here it does.
greater than 1, less than 1, all right? No, actually, let me do this first. Imaginary part of the dielectric function. At the resonance frequency, let's put it there.
And let's think capital B.
There's absorption in the material. And then what's the response? You know, what happens to the real part when we look at that? We find that the real part is greater than 1 at very low frequency. It's really easy for the material to respond, right? At extremely high frequency, it's 1, right? And then in between, it does that. Okay? The real part of the dielectric function is actually less than 1 over some region. The region where it's less than 1 is where there's actually absorption. There's absorption everywhere here, but there's significant absorption in there. And as a result, you can't propagate the wave to send information from one side of a sample to the other because there's absorption loss. Right? So it turns out that the actual signal velocity, information, still travels, well, okay. There are two things that need to be considered. There's absorption and there's dispersion, right? Meaning that the speed with which the wave travels depends upon frequency. So I actually should put here, that's epsilon 1 and epsilon 2. I should also plot the measurable things, which would be the index of refraction. That's the thing that we're interested in as far as the speed is concerned. There's 1. And the index of refraction looks like that. Yeah, it's less than 1. It is. There was a material science professor who discovered this, one of our faculty, about 15 years ago, and attempted to patent a material in which the speed of light would be greater than c.
What happened?
Before he got out the door, the patent memo went up the line, and before the institute patents something, they send it back down the line to be checked. And a physicist said, duh, and duh. That, yes, the index of refraction is less than 1, but no, you can't send a signal from one side to the other. If I have time, at the very end of the course, I'll come back to group velocity as opposed to phase velocity. This is the phase velocity. And the extinction then looks like that. Okay? So, and by the way, I regularly, we used to do this. Actually, we haven't done the experiment in a while. We use the fact that the index of refraction of materials is less than 1 in the X-ray regime, for example. One complication here is that I just drew a single oscillator. And what do real materials look like? Real materials are going to have oscillator after oscillator after oscillator, each one at different frequencies, usually due initially to the electronic excitations and then to the vibrational excitations of the material. So a real index of refraction as a function of frequency looks something more like this. And so on. Every single one of these corresponding to a particular oscillator in the material. Vibrations, electronic excitation. And then finally you get out, and then you actually get oscillations due to electronic excitations in the material from the M shell to the vacuum and so on, right? So you get more of these out here, all on top of each other. And then eventually it settles down. You get all the way out there. And the index of refraction at very high frequency X-ray regime is less than 1. But what it is about 1 minus 10 to the minus 6. All right. But that's that value is such that if you come in at a glancing angle, you can get total external reflection for angles below about a half a degree of incidence from the surface. 89.5 degrees from the normal. That was more than I intended to tell you.
It was interesting.
Okay, so dielectric functions look like that. Yeah, Adam.
If you shine a light with the full spectrum from a very long wavelength, very short wavelengths,
Yes.
would it be like a filtering effect of some sort at the other end?
There's all sorts of really, really neat things that you can do with the dispersive index of refraction, right? Where, and this has been done. I think for homework, I gave you the pulse, right? You have a pulse that turns on and turns off. What you're going to do is you're going to find out, I think I made it a very short pulse, 6 cycles, right? That 6-cycle pulse has got a very broad spectrum of wavelengths in it. Think of it as it is a Fourier transform, right? It's got a broad spectrum of wavelengths. So I don't remember whether I asked this. If your pulse, let's say, is centered in the mid-visible, let's say yellow, right? Then you can ask, now if I chop that pulse really short, what do I see? And the answer is you see white, because all of the colors of the spectrum end up being included in the short pulse, right? Now what you can do is you can take that very broad spectrum white pulse, and you can pass it through a material, and you can tear it apart into its wavelength components, because long wavelengths will travel faster than short wavelengths when they pass through the material. Because we're almost always on this side of the resonance. We're on the low frequency side of the resonance, right? And of the electronic resonances, at least. So, and then actually if you look at it, you just pick out a segment, let's say the red portion of the pulse after it comes through. It turns out that that's much broader because of the fact that you selected a wavelength, a specific wavelength of the segment. But in optical communications, pulses get pulled apart by index of refraction, and then you shift to a new material with a different dispersion, and you take the pulses and you push them back together again. You can select portions of the wavelength. There's all sorts of stuff that you could do in order to control how you send information through a system. And I'm hoping that that will be the topic of next semester's course, Optical Properties of Materials. I have the whole course laid out in my head. Let me turn off that for a minute.